Okay, hello everybody. Welcome to this lecture number 7 in calculus. So our theme today is section 1.4.2 of our lecture notes, which is about the technique of integration by parts. Just before we get into that, I'm going to just look at an example that we didn't quite get to last week, just by way of a little review of last week's main content, which was the substitution technique for integration. So I'm just going to turn this over so that I can write on it. Okay, so here's just an example, which is actually in last week's slides. It's one that we didn't make it to in last week's lecture, but the example was basically this one. So it's it's yet another typical integration problem. We're asked to basically integrate this function 1 over x plus square root of x from 1 to 4. And so again, as often with these kinds of examples, they tend to be sort of thrown at you out of the blue. We have no particular context for looking at this particular function, except that we're asked to find an antiderivative for it. And that's not easy. I mean, this thing is it's not too bad, 1 over x plus the square root of x, but how would we possibly go about writing down something that has that as its derivative? That's the problem that we're faced with. And glancing at it, we're building up this sort of toolkit of techniques. The main technique that we have so far is the substitution technique. And the advice when you're looking for some opportunity to use the substitution technique is to find some element in your problem that you want to call u with the property that the derivative of u also appears somewhere in your problem. Because we want to rewrite our problem in terms of u, including rewriting the dx part in terms of du. And this one, it just doesn't look like a candidate for that either, because we don't have a product, we don't have different factors. There's really no obvious thing to write as u. We can write x plus the square root of x as u, but when we write down the derivative of that, it won't really help us. We get something like 1 plus 1 over square root of x. So what can we do? So, and this is really, it is kind of experimental. There's no methods that are guaranteed to work. But one thing that you can try to do, if it's not obvious that you can deal with the thing as it appears, is we can try writing the expression as a product. See if that helps us somehow. I guess it's all a bit speculative, but maybe it will. And one thing that we can do there with the denominator in that product, in that problem, is we can write it as 1 over square root of x times square root of x plus 1. And ask ourselves, is that any better? We can do it. And well, okay, it's kind of a bit better maybe in the sense that at least it's written as a product now. And when you're trying to integrate something that's a product, sometimes that's where the substitution technique can apply, because maybe one factor can be called u, and the other factor might appear somehow in the derivative of u. So what do we have? We've got a square root of x plus 1 factor, and we've got a square root of x factor, both of which appear in the denominator of a fraction. So at this stage, we're still sort of on the lookout. Is there some substitution that we could try? And I guess if we think about the square root of x, we know that the square root of x is x to the power of 1/2. So the derivative of that is basically, more or less, x to the power of minus 1/2, which is 1 over the square root of x, which is something that appears in our problem. So we've got a 1 over square root of x here. We've got a 1 over as well, but the square root of x plus 1 here. So a suggestion is to try writing u equal to square root of x plus 1. Okay, it's not obvious in advance that this is going to work, but we might observe that when we look at du dx, it's got 1 over the square root of x in it, this bit that's circled. So maybe there's some possibility to absorb that somehow into the du dx. Okay, let's try it. So du dx, this is obviously x to the power of 1/2 plus 1, which is sometimes a handy way to write it if you want to differentiate. So du dx then is 1/2 x to the power of minus 1/2. The 1 gives us 0 when we differentiate it. So that's 1 over 2 times 1 over square root of x. Okay, that's kind of promising, because we do have a 1 over square root of x in our problem that's, that we would like to deal with. So that can actually be absorbed into a du if we try to rewrite the problem in terms of this u. The other part is just 1 over u, so that we can deal with. So this is saying, in terms of the substitution technique, that okay, the 1 over 2 is just a constant that's hanging around. We can deal with that. Just kind of doing this sleight of hand of pretending that this thing's actually a fraction. We would write this as 2 du equals 1 over root x dx. And the good part of that is that 1 over root x dx is there in our problem as it stands. And what's left when we rewrite that is 2 times du is just 1 over u, which is again something that's writable in terms of u. So our integration, well actually also while we're at it, maybe we should write the limits of integration in terms of u. So when x is equal to 1, u is the square root of x plus 1, so it's the square root of 1 plus 1, which is 2 for the lower limit. And when x is equal to 4, which is the upper limit, then u is the square root of 4 plus 1, which is 2 plus 1. So our upper limit becomes 3 when we write it in terms of u, and our lower limit is 2 as a value of u. So our problem becomes, when we rewrite it in terms of u, we've got an integral from u equals 2 to u equals 3, and I think it's actually a good habit to explicitly write here u equals 2 and u equals 3 rather than just 2 and 3 to make it completely clear to yourself and anybody reading it that you're talking about values of u. The 1 over root x dx part is 2 times du, so we can put the 2 outside and write the du. And then what's left is just 1 over u. So we have translated our problem from this nasty thing involving fractions with square root of x at exit to just 1 over u. Antiderivative for 1 over u in general is log of the absolute value of u. Here we're only dealing with positive values of u, so we can just write log of u. There's a 2 still there outside. From u equals 2 to u equals 3. So that's just 2 times log of 3, plugging in u equals 3, minus 2 times log of 2, which if you want to, you can write it as 2 times log 3 over 2. You can leave it the way it is if you want to as well. But that is the answer to the problem. So it's just another example on substitution. And I suppose the point that I try to make here is, sometimes when somebody hands you an integration problem like this, and it's really not clear what you can do with it, it's probably that there's some substitution that can be applied if you factorize the expression in some way, or if you find some way of writing it that admits some kind of substitution. Not necessarily always, and it's extremely easy to make up examples of integration problems that you just can't really solve at all in terms of finding antiderivatives. But if one is presented to you in a calculus textbook or in a lecture, there probably is something that will work. And quite often it'll involve a rewriting or a reorganizing of the expression so that you can express it maybe as a product of 2 things. And after that, maybe you can see some substitution that might work. So this one, I think, is a tricky one. It is from an exam paper in this course back. I think it was back in 2013, which seems recently to me, but probably not to you. But it's a tricky one, I think. So it's got the nice feature that once you figure out what to do, it's kind of clear that you're on the right track, but it's quite tricky to spot what exactly you can do with that. So I guess we're going to look at some more techniques this week. But I guess in most cases where it's completely not obvious what you should do, like this one, it's usually some substitution after some rearrangement of the statement that'll work. Okay, does anybody have a question or a comment about that one? That's really just to recall sort of where we were last week and what we were doing. We're going to move on now and look at a different class of problems altogether. And this week our theme is what's called integration by parts. Okay, and here it's essentially it's another technique for integration. And unfortunately, integration problems don't come with a flag telling you what technique you should use. We have to use our ingenuity for that. But in the way that the substitution technique is basically a reversal of the chain rule of differentiation, the integration by parts technique is basically a reversal of the product rule. So let me try to explain again by means of examples what that's supposed to mean and how exactly that works. So we'll start first with a sort of ad hoc example, which we'll solve by kind of staring at it and reverse engineering solution. And then the kind of theme for the lecture, I suppose, is how we kind of might organize this technique so that it's not quite as ad hoc as it appears in the first example. So let me see. Okay, so I'm going to write this again. So here's an example, example 24, find integral of x cosine x. So again, this doesn't look sort of too bad. It's a product of 2 relatively nice things, x and cosine x. But on the other hand, we've got initially no idea how to deal with it. So if you think about substitutions, which would often be the first port of call, so So there's nothing that we can substitute there. I mean, if we try writing u equals x, the derivative of u then is just 1. That doesn't help us at all. If we try writing u equals cosine x, the derivative then is minus sine x, which doesn't appear anywhere in our problem. So there's really no way that we can sort of use that usual process of trying to translate the problem into a problem involving u. So, okay, that doesn't really look like a candidate for substitution. So we must ask ourselves, well, what can we do then? And so I suppose the first question is, the frame of mind to put ourselves in is, how could that expression x cosine x arise as a derivative? What kind of thing could it be the derivative of? And okay, well, we know that cosine x is the derivative of sine x. Fine. So x cosine x then might be sort of something like the derivative of x sine x. That's kind of a, not great guess, but a better than nothing guess. So maybe if you try x sine x, if we differentiate x sine x, well, x sine x is the product of two functions of x. So to differentiate it, we have to use the product rule. So what we're using here is the product rule for differentiation. And that would tell us that we should take x multiplied by the derivative of sine x, which is cosine x. Okay, that's great. That's actually what we want. That's really good. But there's another term, which is sine x multiplied by the derivative of x. So the derivative of x sine x, if that's our first kind of candidate guess for an answer to this problem, is kind of nearly right. It's x cosine x, which is exactly what we want, plus this other term that we don't want. So to compensate for that, we should just subtract off something whose derivative is sine x, and that will kind of cancel this sine x out of our problem, and hopefully give us something that does exactly the job we want. So sine x, we can observe, is the derivative of minus cosine x. Okay, that's just an observation. We know that if we differentiate cosine, we get minus sine. So if we differentiate minus cosine, we should get sine. So basically, if we take x sine x as our first guess for an answer, differentiate that, we get x cosine x plus sine x. In order to get rid of that sine x term that we don't want, we should add into our proposed solution something whose derivative is minus sine x, and that would be cosine x. So the conclusion then would be that the derivative of x sine x, of x sine x plus cosine x, what would that be? Let's just calculate it to make sure that we get it right. The derivative of x sine x is x cosine x plus sine x. That's from applying the product rule to x sine x. And then the derivative of cosine x is minus sine x. So sure enough, we can cancel off the bits that we don't want, and we're left with exactly what we do want, which is x times cosine x. So our conclusion would be, as written there at this stage almost illegibly, is that the general antiderivative for x cosine x is x sine x plus cosine x plus constant of integration. So that's that's a sort of direct approach to trying to find to solve that indefinite integration problem by sort of trial and error. As we did before, kind of first guess is kind of a bit right, compensate for whatever's wrong with it by adding in some extra term that cancels the bits you don't want, and that does the trick. And I suppose we could sort of argue that what we've done is kind of a reversal of the product rule, in the sense that we made a guess, applied the product rule to that. We got two terms. One of them was what we wanted, the other one wasn't, but we were able to compensate for that, or to deal with it by adding in another term whose derivative would basically cancel it. So there is a kind of a reversal of the product rule going on there, but it's kind of an ad hoc process, and maybe not necessarily a thought process or the kind of trial and error process that you'd want to be going through every time you're faced with a problem of this nature. So really, this example is an introductory one. It's kind of, I suppose, meant to get us thinking about how would we try to systematize or organize some process for reversing the product rule of differentiation. And the answer to that is, well, yes, people have thought about this and they've come up with this technique, which is now known by the name integration by parts. But really all it is a kind of organized version of what we just did. But it is actually useful in that it gives us a kind of framework in which to tackle problems of this type without having to kind of directly engage in this kind of ad hoc reasoning that we just did. Okay, if you have a question at any stage, please just throw it into the chat, or if anything's not clear, feel free to put a comment in the chat or indeed to turn on your microphone. Okay, well, here's a slightly more, well, an indication of how we might kind of manage this process in a bit of a more organized way that would relieve us of some of the experimental thinking from the last example. So what happened in that example was basically the product rule was kind of applied in reverse, but in a sort of reverse engineering way. So a way of managing this process in general is what's called the integration by parts formula, which is the last line in this slide, and definitely something useful to sort of carry forward with you out of this integration course, because it's something that we do encounter from time to time as techniques of integration go. This is one of the ones that really is quite useful and that does turn up around the place. So the product rule of differentiation tells us, and here it is written in a shorthand form, it's a very nice thing. It tells us that if we have a pair of functions, u and v, both functions of x, and if we want to look at the derivative of their product, this is the so-called Leibniz rule for products. The dashes here indicate derivatives with respect to x. The product rule of differentiation tells us that the derivative with respect to x of the product uv is given by the derivative of u multiplied by the function v itself, plus the derivative of v multiplied by the function u itself. So it's quite a nice thing to apply, and it obviously applies to a whole load of situations. And it means that if we know how to differentiate both u and v independently, then we know how to differentiate their product, which is nice. Okay, so what we'd like to do would be to have some kind of version of this for antiderivatives. Okay, and you sort of looking at the right-hand side and saying, well, the antiderivative of this thing on the right is uv is great, except that it's kind of very limited use because it's very unlikely that the thing you want to find an antiderivative of is already going to be presented to you in the form u dash v plus uv dash in a recognizable way. So, great if it is, but it's not really very likely to happen very much. So instead of just saying that, we want to try to organize it a bit better. And so the first suggestion here is this: what's written here in the next line has exactly the same meaning as what's written in the previous line, except that it's just emphasizing moving from a function to an antiderivative rather than to a derivative. So if we integrate across the equation here, okay, then so we're just sticking an integral sign in front of everything basically. We're saying that if the two things on both sides of this equation are equal to each other, then their indefinite integrals are equal as well. So this is saying the indefinite integral of uv dash is equal to the indefinite integral of u dash v plus indefinite integral of uv dash. So that's just a unnecessarily complicated rewriting of the product rule. But when we think about what all these things mean, uv dash is the derivative of uv. So its antiderivative is just uv. Okay, so essentially the dash here and the integration sign pretty much just sort of reverse it to cancel each other, because we're integrating the derivative of something, we just get something back. So this is saying that uv is the indefinite integral of u dash v plus the indefinite integral of uv dash. Okay, the plus constants of integration, I guess, but they're all kind of imagined to be implicit there in the integrals. Okay, so this is again just a restatement of the product rule of differentiation in sort of integral form. And if we rearrange it, we can write it as integral of uv dash over x, which is the last term here, we're leaving that on one side, equal to uv, the product of u and v, minus integral of u dash v dx. And this is what they call the integration by parts formula. Okay, it still looks a bit useless until you see how it works in practice, so which is what we're going to do for the rest of our next 20 minutes or so today. It's the same statement as the product rule of differentiation. It looks worse, but it's really the same. And how to apply it, I think, is not obvious. But basically, the way that we can apply it is that if we're presented with an integration problem, which we kind of imagine to be the left-hand side here, so the product of two things that we call u and v dash, then basically what this is saying is we can rewrite that problem as a problem of integrating u dash v instead of uv dash. Okay, and of course, depending on what the u and the v are, it's questionable whether we can actually even do this in practice. But if we can, then we might be hoping that the integral on the right is an easier one to deal with, maybe, than the one that we started with on the left. That's the strategy. And okay, sometimes it works. The UV is here as well, but it doesn't really cause a problem because it doesn't need to be integrated. So it's kind of, it's certainly part of the solution, but it's not something that we have to really do anything with once we write it down. Okay, so that's the idea. This is kind of supposed to be a theoretical description, which might make more sense after we look at an example. So let's do that. Okay, so here's the first example again, but handled according to this integration by parts formula. And maybe a good idea would be to write down the integration by parts formula there in the heading. So what it tells us is that integral of uv dash is uv minus integral of u dash v. So the idea here being that u and v dash are sort of factors in a problem that we are presented with. So here's our problem again, x cosine x. Okay, so certainly this, once we get a hang of this thing, we will recognize that it looks like a candidate for integration by parts. The thing that we want to integrate is a product of two factors. One is x, the other one's cosine x. Both of those things individually are sort of manageable. Okay, so our strategy to implement the integration by parts technique on this problem would be, we should take these two factors, x and cosine x. We should refer to one of them as u, and the other one as v dash, which means the derivative of some v. Okay, then we should write down our u and our v dash. We should write down the corresponding u dash and v, which would be an antiderivative for the thing that we called v dash. And then we should plug all that into the integration by parts formula and hope that we can deal with the integral that's now on the right-hand side of it. Okay, and of course, there's a choice here to make. You've got two factors, and you have to decide which one are you going to call u and which one are you going to call v dash. Okay, and the thinking here that should guide us is we're going to be replacing the problem of integrating uv dash with the problem of integrating u dash v. So instead of u, we're going to be dealing with its derivative u dash, and instead of v dash, we're going to be dealing with an antiderivative v for it. So we want to label u and v in such a way that the u part, the one we call u, is something that gets nicer when we differentiate it, so that we'd rather be dealing with u dash than u itself. And the other part that we call v should be something that doesn't get too much worse when we take an antiderivative for it, because that's what we have to deal with. Okay, so the suggestion here, and maybe we'll rationalize this more at the end and look at the alternative, is to take u to be x and v dash to be cosine x. Okay, then the problem that we're faced with is to integrate uv dash, which fits into the left-hand side of the integration by parts formula. Okay, having written down u and v dash, write down u dash. Well, u dash is just the derivative of x with respect to x, which is 1. Okay, that's good because u dash is nicer than u. And write down an antiderivative for v. So if v dash is cosine x, then an antiderivative for that is sine x. And here we don't have to bother with a constant of integration. We only need one antiderivative. We stick the constant of integration in at the end. Okay, so if v dash is cosine x, then an option for v is sine x. And that's certainly no worse than cosine x. So this looks kind of good. U got nicer, if anything, when we differentiated it, and v dash didn't get any worse when we took that antiderivative. Okay, and now we've written down also, as well as u and v dash, we've written down u dash and v. Okay, so the integration by parts formula tells us that we should rewrite uv dash, the integral of uv dash, as uv. Well, u is x, v is sine x, so that part is x sine x, minus integral of u dash v. U dash is 1, v is sine x, so that's just minus integral of sine x dx. And that's good, because we know what we know an antiderivative for sine x is minus cosine x. So this is x sine x then, which is the uv part, minus antiderivative for sine x is minus cosine x, so it's minus cosine x, and then plus constant of integration, of course, which is always a part of our solution to any indefinite integration problem. So that's the integration by parts formula, and you know that's sort of how it works. And I guess as with all these techniques, the way to get expert at them is by practicing with examples. And the thing to practice here and to be on the lookout for is the kind of acumen in figuring out which of the factors should you call u and which should you call v dash. And just to highlight that in this example, you know, the alternative here would have been to call, if we had written u to be cosine x and v dash to be x, which would have been the alternative approach in implementing this formula, then u dash would have been minus sine x, which is all right. That's not any worse than u. But v would have been x squared over 2. And we would have, instead of swapping the problem of integrating x cosine x for the problem of integrating just sine x, we would have been swapping it for the problem of integrating x squared sine x, which, if anything, is worse than what we started with. So, in this integration by parts technique, there are usually sort of two alternatives, and quite often one of them is good and helpful, and the other one can, if anything, make matters worse. So and the sort of hint, I guess, is to choose u to be the one that gets nicer when you differentiate it, if that's an option. And for example, if you can be a power of x, then the degree will go down when you differentiate. So that can be quite fruitful in this business. So if we had taken this alternative, we would have ended up with the problem. The problem of integrating u dash v, which would have been something like x squared sine x or x squared sine x over 2, which, if anything, well, it definitely is actually sort of worse than the thing we started with, which was x cosine x, because it's got a higher power of x on it. So that would not have really worked out well for us. Okay, so, but, sometimes it's not completely obvious in advance which way it will work. And in that case, trying one of them and finding that it doesn't work can give you the idea of trying the other one. Okay, so that's it. That's a very typical, I suppose, relatively straightforward example of the integration by parts technique. Does anybody have a question about that? Okay, if not, then let us proceed. But yes, here's another one. This is another very standard integration by parts example. And I suppose one of the things in calculus that we like to do is there are certain sort of standard functions that we like to work with, including polynomials, rational functions, square roots and other powers, trigonometric functions, and exponential and logarithmic functions. And you might wonder, is there an antiderivative for log x that we can write down easily? It would seem reasonable to think about that question, since log x is such a fundamental function of calculus. And that's sort of not, well, kind of yes and no, not really. It's not something, the antiderivative of log x is not something that's on the top of everyone's mind, I think, generally. But yes, we can actually use, surprisingly, the integration by parts technique to find an antiderivative for log x. And of course, one of the remarks about log x is quite a mysterious function. I mean, in a sense, it arises as the antiderivative of 1 over x, which is a relatively everyday kind of function, but one that doesn't have an antiderivative that can be written in terms of just powers of x. So, in some way you sort of have to almost, well, one way of describing the meaning of the log function is as an antiderivative for just 1 over x, which is a power of x, but doesn't fit into the framework for taking antiderivatives of powers of x. So is there something whose derivative is log x that we could write down easily? So that's doesn't have an obvious answer. We do know that the derivative of log x itself, so let me stick this into the notes here, the derivative of log x itself is 1 over x. Okay, so log x is certainly an example of something that gets nicer when you differentiate it, in the sense that 1 over x is a familiar function that we've all been working with since we were children, and log x is something that you only encounter if you study mathematics to an advanced level. So, 1 over x is certainly a more manageable, sort of nicer thing to deal with than log x is. So, but what would you have to differentiate to get log x? That's not really something that has an answer that we can quickly give. So if you were presented with this problem, determine an antiderivative for log x, how could you go about it? There's no substitution that you could try because there's only one thing in the expression. It doesn't really look either like a candidate for integration by parts because it's not a product. And integration by parts technique applies to things like this, integral of uv dash. And it says that the integral of uv dash is uv minus integral of u dash v. Sorry, I've just written that down for a second time. It's already written here. So it doesn't really look like a candidate for that either. But we can always write it as kind of 1 log x. And think of it that way, as a product. Why? Well, because you could apply the integration by parts formula and amazingly it works. So here the thing to do is to take u to be log x, which isn't obvious, and take v dash to be 1. And I guess the rationale for that is that you find out afterwards that it works. But before that, u is something that gets nicer when you differentiate it in terms of becoming more familiar, more manageable. So if you write log x as 1 times log x and apply the integration by parts formula with u equals log x and v dash equals 1, what you find is that u dash is 1 over x and v is just x, because v is an antiderivative for 1, which is x. And that sort of looks kind of more familiar ground, at least, than looking at u and v dash, which is this log in it. So if you do that and plug it all into the integration by parts formula, see what comes out, and see if you can deal with it, this is saying integral of log x, which is 1 log x. So the 1 there is the v dash, and the log x is the u. That should be uv. U is log x, v is x. So the uv part is x log x. But we don't have to do any more integrating with that. It just stays as it is. And then we have minus integral of u dash v, and u dash v is just 1. So integrating that is no problem. This is just integral of 1, which is x. So we end up with, as an antiderivative for log x log x minus x plus constant of integration. And of course, we can again easily check that this answer is right by just differentiating the right-hand side of it. And of course, when you do, I think it's actually worth doing if this technique is new to you, because when you do that as well, there's a kind of added advantage that you kind of see how this process has reversed the product rule. And certainly if you differentiate the right-hand side here, you get x log x, you get x times 1 over x plus log x from applying the product rule to x log x. And then so you've got 1 plus log x and then minus the derivative of this x, which passes the 1, and you're left with just log x. So yeah, so I suppose it's an example. I mean, this is a classic example that's in all the textbooks. And to be honest, there aren't like 100 more examples like it. It's kind of a special one. But it does show us that sometimes problems which aren't really obvious candidates for the integration by parts technique can actually be handled using this technique. So it's a nice one and kind of worth having in your repertoire as well. Okay, anyone have a comment or a question? Okay, if not, then on to the next ingredient of integration TV, which is high entertainment. Okay, to highlight that there's a few other things that I suppose crop up in this business of integration by parts. One is that sometimes one application of the integration by parts formula is not enough and you need another one. And this is, again, another sort of classic example. You'll find examples like this on old exam papers, countless examples of them, to be honest. This is another classic one. So if you've got some power of x multiplied, let's say, by an exponential or a trigonometric function, this is classic integration by parts territory as well. And the thing to notice here, I suppose, is, again, it's not a candidate for substitution, because substitution u equals x squared or u equals e to the x is not going to get us anywhere here. The two factors in our problem, neither of them resembles at all the derivative of the other, which is what you would like to see for a substitution strategy to work. But it is kind of clear territory for integration by parts because we've got two factors, x squared. Now, x squared is basically something that gets nicer when you differentiate it because the power goes down on the x. And e to the x is something that doesn't get any worse when you take an antiderivative for it. It just stays exactly the same. So, trigonometric functions, which just kind of alternate between sine and cosine, and exponential functions, which stay exactly as they are when you take antiderivatives for them, are the sort of things that turn up as v dash in integration by parts problems. So here again, sort of good candidate for integration by parts. If we take u to be x squared, then u dash is 2x, which is nicer because it's a lower power of x. If we take v dash to be e to the x, then v is also e to the x, which is no worse than v dash. So kind of replacing u and v dash here with u dash and v looks like it might make things better. Okay, and if we do that and plug it all into our integration by parts formula, we get that the integral of x squared e to the x is uv, which is x squared, that's u, e to the x, minus integral of u dash v, which is 2x e to the x. Okay, so we're not done because we still can't integrate this bit. But somehow we've managed to kind of reduce it from x squared e to the x to x e to the x, which is progress. Okay. And we might observe that, okay, what we have to, so basically our problem now that we're still left with is to calculate an antiderivative for x e to the x, we've gone from x squared e to the x to that. And we might say, well, by applying the integration by parts formula again to this, we can reduce the power on x from 1 to 0. So we can just, we can just we can get rid of the x altogether, which is exactly the strategy. So I suppose the point here is, this is just an example with x squared in it, but by repeatedly applying the integration by parts formula to something like this, you can sort of reduce the power on the x part repeatedly until you get it down to 0. And you could even kind of write down a sort of recursion formula for some power of x to the n times e to the x. We'll just do one that requires 2 rounds because I think that's enough to illustrate the general principle. So our problem now is this is the thing we started with. We've managed to rewrite it as x squared e to the x minus 2 times the integral of x e to the x. And here at this point, I think when you're keeping track of things and you're trying to write down what's going on, there is a sort of process of having to deal with one integral at a time and not wanting to carry around with you all the bits and pieces. So maybe giving a name to the part that you're trying to deal with is sometimes a good idea. So this is an I. It doesn't really look like an uppercase I in this font, but it is. So we're just going to give the name I for integral to integral of x e to the x. And so to calculate that, so that doesn't really look like an I. I should change the name of it to something else. So to evaluate I, we can apply the integration by parts formula a second time. And here again, we want u to be the thing that will get nicer when we differentiate it. So take u to be x, take v dash to be e to the x, then u dash equals 1, v equals e to the x. These are not the same u and v, of course, as on the previous slide, because we're just dealing now with this piece I. So try not to let that confuse you. And if it does, just give them some different names. And so then I, according to the integration by parts formula, should be uv, which is x e to the x, minus integral of u dash v, which is just 1 e to the x. Integration e to the x just gives us e to the x. So this is just x e to the x minus e to the x plus constant. And so finally, our problem was, from the last slide, we had that integral of x squared e to the x was x squared e to the x minus 2I. And now that we know what I is, we can write that as x squared e to the x minus 2 times x e to the x plus 2 times e to the x plus constant of integration. So it's another very typical sort of scenario where a second round of integration by parts might be needed to kind of simplify the original problem enough that you can actually solve it directly. But that's one that we can do. I won't ask you anything else x squared in an example like this, but obviously there's nothing really special about 2. If it was x cubed e to the x, the first round would reduce it to x squared, the second to x, and the third one to just 1. So yeah, so this integration by parts formula. I suppose it's of these techniques that we have, it's kind of in a way the most organized one. It resembles the rules of differentiation a bit more because a bit more than the substitution one does, because we have this kind of integration by parts structure that we can plug everything into, and we're still left with the problem at the end of evaluating an integral that hopefully is easier than the one we started with, but that still might require some ingenuity to solve. But hopefully these examples are not too bad. Okay, I'm going to thank everyone who's joining us for the recording at this point and close the recording. That's our last example for today. So thanks everyone for joining us.